All right, let's start talking about chapter 33, particle physics. So we'll talk about the early states of the history of particle physics, describe the four basic forces, how accelerators are used to create particles, to study them, what we notice about particles, the conservation laws. Is the quark the most fundamental particle? That is the question. And then the investigation of unifying the fundamental forces. Okay, so an introduction to particle physics. When you zoom in on a solid, you get to a molecule. When you look at one of the constituents of the molecules, you see this nucleus with these electrons orbiting it. You zoom in on the nucleus, you see that a proton is actually made up of these little guys called quarks, and you can see in here that these quarks are exchanging gluons. And gluons are what bind the forces of the quark together. And there, if you look at a single quark, you can see the gluon and the quark talking to each other. Okay, so particle physics is the study of basically the quarks and the other fundamental constituents of matter. If you just study the nucleus, that would be nuclear physics and chemistry above that. But if you want to study the actual particles themselves, the most fundamental constituents of matter, that is called the field of particle physics. Okay, so Yukawa predicted this particle called the Yukawa particle. It is now known as the pion, and he predicted that it must exist based on some of the conservation laws that when they were studying these particle interactions. And there's a really interesting relationship between the time a particle lives and its mass. And so basically we look for the measurement of a particle. In order to measure it, we basically measure what's called its resonance or its lifetime. And by measuring the lifetime of a particle, we can get its mass. So what this is saying is the larger the mass, the greater the energy, and the greater the energy, the shorter the time it can exist. So heavy particles don't live very long. So we look for these particles in detectors by measuring their width, we call it, their lifetime, in order to get their mass. So, for example, if you see a particle decay in this amount of time, then you can get its energy to be 100 MeV. And so that means that the mass of the particle must be about 100 MeV because it only lasts 3.3 times 10 to the minus 24 seconds before it decays. Okay, and so yeah, so here's some masses of the other particles there. So the four basic forces of matter, you have the strong force, which holds quarks together inside the nucleus of the atom, holds quarks into protons and neutrons. The gluon is the force carrier for the strong force, and that means if you have a quark and another quark, the way the quarks talk to each other is via a gluon exchange. The weak force, which is radioactive decay, is mediated by W and Z bosons. The carrier particles here are all bosons, B-O-S-O-N, which is short for Bose-Einstein. And then electromagnetic force is basically everything else in the universe, and the photon mediates that. And then we theorize that the graviton is the particle which mediates the force of gravity, but we're not really sure. But gravity is the longest distance force. It acts across the universe on all matter. Okay. This is an example of a Fineman diagram. And in a Fineman diagram, you can have time and space on this axis. You could swap them around if you want. But basically this says that two particles collide and scatter off each other. And they scatter off each other by exchanging a photon. And so that's what we say when we say that a particle mediates a force. This would be an example of a positron scattering off a positron and exchanging a virtual photon in between. Now, this Feynman diagram is just like a free body diagram for regular forces. At each of these intersections is an equation, and each of these intersections, the result of the equation is a probability of that interaction occurring. And so when you calculate this, what is the probability of this particular interaction happening, you write down the equation that each of these, we call them vertices. Vertices. Does that look like vertices? Vertices. Vertex, plural. Each of those has a calculation. This is called the theory of quantum electrodynamics. Anytime you have a photon involved, it's QED, quantum electrodynamics. And every one of those pictures has a particle. This is an example of QCD, quantum chromodynamics. This is a Fineman diagram for that. We call it quantum chromodynamics because now we're talking about, instead of electrons, we're talking about protons and neutrons, which have quarks, which means they talk to each other via the strong force. And so in this case, you could scatter a proton and neutron off each other, and the particle that will be doing the exchanging will be the gluons, and they will be showing up in the form of a pion. That's just an example of Fineman diagrams. Again, at each of these vertices are calculations, and those calculations give you the probability of the interaction occurring. So in order to test those theories, we use accelerators, and accelerators create mass from energy. So you have E equals mc squared, so we smash particles together, and all that means is we put them into higher energy states so that we can create higher matter particles to understand how the universe works. There's a couple of different types of accelerators. There's a Van de Graaff accelerator, which just rubs a belt against a piece of metal or something and then deposits charge. And then when you have that, if you touch that, it'll shock you. You can also put that electricity down a beam line and make those electrons hit something and then see what comes off at the target. Van Allen Hall had a massive 7-story Van de Graaff generator and a target area that studied the nuclear construction of atoms in the 60s, 70s, 80s, and 90s until it was taken down to build Biology East in, I think, 1997. There's another thing called a cyclotron. This is what's at the basement of hospitals to generate their isotopes for PET scans and other radiology type things. And basically you have an electric and magnetic field pulsing here, and then you get the electron to accelerate, and the faster it goes, the larger its radius, the more energy you put into it, until actually it's going to go this way until it shoots out of the thing, and when it shoots out, you have it hit a target to generate that isotope. Colliders like the Tevatron at Fermilab or the LHC in Geneva, Switzerland, they use magnetic fields to put the beams in opposite directions, and then every now and then they have them collide and at this intersection point, and that's where you end up getting that very high energy states. So the biggest accelerator right now is the LHC in Geneva, Switzerland. It's 300 feet underground, very high energy accelerator, 7 TeV of collision energy, so the center of mass energy was is 14 TeV. It's currently shut down for a short period for upgrades. It'll be back on in another year or so. The superconducting super collider was being built in Texas. It was designed to be way more energy than the LHC. The LHC was actually retrofitted in an old experiment called LEP in the 70s and 80s, whereas the SSC was going to be built from scratch in Waxahachie, Texas. And then when Bill Clinton was elected, there was a massive push to cut spending, and so the Congress axed the program after a quarter of the beam line had been dug. Similar thing, 300 feet under Texas, and they built basically all of the upper infrastructure. It was a very sad day. That was 1993 when they killed it, and by 98, 99 we would have discovered the Higgs boson, but we didn't discover it until 2012 after the LHC decided to do its upgrade, since the United States was not going to go through with its promise to build the SSC. Okay, so a linear accelerator like SLAC in Stanford, the Stanford Linear Accelerator Center, it's a 2-mile long tunnel, and it's just a big tube of magnets, and they just shoot their particles at a wall, basically, and see what comes out. Lately, they've been studying molecules and things like that, trying to put molecules in quantum entangled states and things like that. Okay, so Dirac is an amazing man, abused by his dad, but very good physicist, and he predicted antimatter. So for every particle, there's an antiparticle. That's one thing we've noticed. It seems to be every time we create a particle, we have to create an antiparticle with it, which is one of the issues with the current understanding of our universe, is that why is the universe filled with matter and not antimatter? So the universe must prefer one over the other. So this predominance of matter over antimatter is a question, big question. The hadrons and leptons are two types of particles. Leptons are things like the electron and the muon. They don't experience the strong force. They mediated by the electromagnetic force. Hadrons are any particle made of quarks, so they experience the strong nuclear force. So, for example, a lepton would be a muon or an electron. A hadron would be a proton or a neutron, or even the pion that we talked about. The bosons are particles that have an integer spin, whereas a fermion is a particle with a half integer spin. And again, the bosons are named after Bose and Einstein for their Bose-Einstein statistics that they discovered, and then which is the statistics of the behavior of these particles. And Enrico Fermi is who's the spin half particles are named after fermions. So fermions obey the Pauli exclusion principle. Bosons do not. So all of the force carriers are bosons. So, for example, photons can be superimposed upon each other, whereas electrons cannot. And that's an example of this Pauli exclusion principle applying to electrons but not fermions. So electrons cannot occupy the same state. That's why chemistry works, whereas photons can, and that's why you can superimpose photons onto each other. For example. Okay. Let's see. Blah, blah, blah. Okay, so here's a list of some select particles and their characteristics. So the gauge particle, photon, that's kind of a weird thing, weird description of the photon. Other bosons, so you got the W, U, Z, and the photon, and this book must not be updated yet. There's also the Higgs, which probably when this was originally published, it wasn't a particle yet, because I don't see the Higgs in there. The Higgs particle is responsible for mass, and that's why the quarks have mass, for example. Not why you or me have mass, but the fundamental particles like the electron and the quarks and things like that. Okay, and then, so these are bosons, integer spin particles. The leptons here are fermions, they're spin half particles. Mesons are, the hadrons, which are made of protons and neutrons, are divided into two groups. The mesons have two quarks, two valence quarks we call them, and then the baryons have three valence quarks. So what that means is that the outer shells of the pion and kaon particles, the pions here and the kaons here, they have two valence quarks, whereas the baryons, like the proton or the neutron or the antiproton and the antineutron, have three quarks that make them up. So that's the difference between the mesons and the baryons. There's zillions of particles. They call it the particle zoo. Zillions of mesons, zillions of baryons that we can create by putting quarks into different states. And there's up, down, charm, strange, top, bottom. So the proton and the neutron, for example, are just up and down quarks. But you can make all kinds of different particles with all the different quarks, whether they're 2 quarks, 3 quarks, etc. So there's some conservation laws about particle decays. There's electron number is conserved, There's muon number. For example, this muon can decay to an electron and then a muon neutrino and an electron neutrino. When I said electron neutrino and the muon neutrino. So there's another particle called a tau, which is similar to the muon. So the muon and the electron and the tau are three siblings in the family, the lepton family, and they each have a corresponding neutrino that goes along with them. So then you have mesons and baryons. There's conservation of baryon number. So if you just look at the baryons here, they either have +1 or -1. These are just kind of stamp collecting things that are a top level view of the interactions of the particles. There's more fundamental rules for why these numbers are quote unquote conserved or the same before and after the interaction, but these make it kind of easy to just do a quick, is this possible, of a thing. Okay, so there's a lot of weird conservation rules. There's Murray Gell-Mann. He just died actually, I think last year. Very smart guy, very cool guy, very chill guy. I once performed at the French Embassy in Washington, D.C. for a very rich guy. And after the performance, he and I were talking, and he said, "What are you doing?" I said, "Well, I'm getting a PhD in physics." And he goes, "Well, we got a few Nobel laureates around here." He's like, "Where's Murray Gell-Mann?" I bet Murray was not there, unfortunately. His name was James Pearl, and he died too a couple years ago. Okay, so quarks, is that all there is? So when we look inside of a proton and a neutron, you see the up quarks, the down quarks. The question is, are there any more fundamental particles than that? We have the atom, and then the proton, and then the nucleus, and the so on, and then the whatever. How do we know that the electron is fundamental, and the all the different quarks, up, down, charm, strange, whatever, are not any smaller than that? And so actually what we look for is one of the reasons we know that atoms, for example, are made of quarks is because you can put them into excited states. And so if you can put them into certain excited states, then you know there must be some structure to them, because the ability for them to have more than one excited state means you're putting each of the constituents into different configurations. The evidence so far with the quarks is that they do not have the ability for an individual quark to be put into an excited state like that. That would imply that it's made of constituent components. So at this point, quarks are it. We don't have any evidence so far. Like we never thought that the proton and the neutron were it. I mean, maybe initially, but the evidence, there was never, once we start looking for the evidence, it was pretty quickly clear that it wasn't the fundamental particle. So we'll see. But at this point, it looks like the quarks, up, down, charm, strange, top, bottom, particles are all the same. Okay, so let's see here. Yeah, so here's some more particles. So you got more mesons here, but it's showing you that it's this 2-quark combination, whereas the baryons are these 3 quarks combinations. All these different particles, the omega minus, the cascades, sigmas, lambdas, deltas, and so on. Let's see, blah. And here was a discovery of the omega minus, which was a big deal. This is a hand drawing of it, but this was a bubble chamber image that they should include in there as well, not just the picture. This is called deep inelastic scattering, shooting particles into the nucleus of a proton and trying to measure the scattering coming out, just like Rutherford. We do the same thing at the LHC, trying to probe deeper and deeper into the constituents of matter. That's the main thing. There's a really weird theory that's part of the quark theory of quantum chromodynamics, and that's the theory of quark confinement. Basically, if you try to separate quarks, if you put enough energy to pull two quarks apart, it just makes two more quarks. And then bloop, you have two more mesons or baryons. So you will always have a meson or a baryon. You can never have a quark by itself. So far, we've never seen a lone quark by itself. They're always in a composite state. And we call this hadronization. When you smash particles together and then you create quarks, they immediately turn into these jets of energy. We call them jets in our detector, or the process is known as hadronization, and it's when it grabs itself and whoosh, shoots out. So the idea here with those four forces is that when you do chemistry, you don't care about the strong force. When you do nuclear physics, you don't care about chemistry. When you're doing chemistry, you don't care about the gravitational effect on your reaction. Gravity has no role in that. So if you can imagine, though, increasing the temperature enough so that when you try to do a chemical reaction, the quarks actually start to affect your outcome. If your temperature is high enough that the quarks are part of your experiment, now you've got a unification of the two worlds. You've got gravity, no, sorry, not gravity, you've got the strong force and electricity and magnetism, for example, affecting each other. And so then, by studying that, you can see how the two forces interplay with each other, and you can create a theory which unifies those forces together, even if at lower energies they're frozen out into different worlds or different aspects and they don't affect each other at lower temperatures. So what we're trying to do, we unified electricity and we unified magnetism together to create electricity and magnetism, and then Murray-Gell-Mann and some others unified electricity, magnetism, and the weak force to create the theory of the electroweak force. And so we have electroweak, the electroweak theory here. Sorry, not Murray-Gell-Mann, that was wrong. It's Weinberg, Glashow, and Salam. They were the big, Stephen Weinberg's a very famous person. So the electroweak theory is basically what's called a unified theory. So at normal energies, you don't see the results of one force acting on another, but at high enough energies, you start to see how those forces can engage, and then you get your things. So this is we looked at this Fineman diagram a little bit earlier, where it was just the proton and the neutron, and then the pi meson, and then the neutron and proton jumped back off. And you can see that actually, in order to calculate that process, you have to consider the actual quarks on the inside. The structure of the protons interacting, the quarks and the proton interacting with the quarks and the neutron, and you can calculate the process. So that's QCD that allows you to calculate that. QCD, QED, the electroweak theory, and whatever together is called the standard model. And that's the standard model of particle physics, which explains all these things. So this is the idea: when you get the energies high enough, your electroweak force and the strong force should unify, and at that point we call that a grand unified theory. We're not there yet. We're looking for that. We're close. We try to get close to this energy at the LHC, but I mean, actually we have 14 TeV, so this is an insane amount of energy before that happens. But the theory of everything is where you need to get before gravity would start to affect your experiments. So we have a long way to go before we can unify gravity in with the other forces and get what the so-called theory of everything. One theory of everything is called string theory or superstring theory, which is a misnomer because it is not a theory, it is a hypothesis. There is zero evidence that it is an actual theory, that it has actual bearing in our reality. And there's a lot of controversy about the amount of funding that string theory gets because they've been promising all these results for so long, and basically they've created a mathematical theory that can take any form you want it to. So it has no predictive power. It's infinitely configurable. So a lot of people have problems with it as a theory, but it's still a beautiful mathematical process. This is the Tevatron at Fermilab. This is the CDF experiment. I've crawled around in there and stole some PMTs out of it. After they turned it off, they let us take them. And I had my film badge on while doing that, and I didn't get any radiation. Okay, so that's your introduction to particle physics, which is the cutting edge of the physics. I'll see you guys later. Bye.